So since the numerical derivative is the derivative of a function at a particular point, how would we interpret that numerical derivative? What is it telling us about the original function?
The slope at that point.
Yeah, the slope of the, and it actually, technically, a curve itself doesn't have a slope, but what it's telling us is the slope of the tangent line at that point. So we're not really finding the slope of the curve, although we usually say it's the slope of the curve because we kind of have an intuitive idea of what it means to be the slope of the curve at a point. But what we're really finding is the slope of the tangent line at that point. All right, so we did some numerical derivatives before. In fact, I even gave you a definition of a numerical derivative, which is slightly different than the limit definition of just the derivative itself. Does anybody remember the limit definition of the numerical derivative?
F of x minus f of c.
Yeah, it's the one that involves the f of x minus f of c. So the numerical derivative, let's try that again. The derivative at some point where x equals c is the limit as x approaches c of f of x minus f of c over, anybody remember? X minus c. There was a question on the test that you took yesterday that you could have used this or you could have used the other one. Most of the time we're actually using the other definition of the derivative though, because usually it's more useful to find the derivative at every point rather than just at a single point. So if we're going to use this definition, let's go ahead and do that here. If we're going to use this definition to find the slope of the square root function at x equals 2, what do I do?
Square root of x minus square root of 2.
Okay, I agree with that, except you're forgetting something. Yeah, so it's going to be the limit as x approaches 2 of, what's it going to be, Tilly?
Square root of x minus square root of 2 over x minus 2.
Okay. Everybody okay with the setup so far? And this is going to be the derivative of f at, at 2. And so we want to evaluate this. There's a couple ways we could approach this. There's one way I like better than another. Any ideas what we could do here? Okay, we could multiply by the conjugate. The problem that we're going to get if we do that, and the conjugate here would be the square root of x plus the square root of 2, right? Yes. Well, yeah, let's go ahead and do that. You want to do it that way?
Sure.
Do you want to do it that way too, Jeremy?
No.
What were you going to say?
Back to the bottom like a perfect square.
Okay, yeah. This is the way I would do it, and it ends up being exactly the same, actually. So we can multiply by the conjugate, and that's what we'll do. But real quick, I'll show you what we can do here. If we treat this as a perfect square and this as a perfect square, then what do we square to get x? Square root of x. What do we square to get 2? Square root of 2. So this is going to factor like this. The square root of x plus the square root of 2 times the square root of x minus the square root of 2. And the reason this works is because these are conjugates of each other. And then what's going to happen, the square root of x minus the square root of 2 is going to cancel with the square root of x minus the square root of 2, and we're going to be able to evaluate it. So that's one way to do it. We would get the same answer as if we multiply by the conjugate. So we'll go ahead and do that. We'll multiply by the square root of x plus the square root of 2. That would be the conjugate of the numerator. Over the square root of x plus the square root of 2. We have to multiply by 1, really. We're just multiplying by 1 here, aren't we? Because the square root of x plus the square root of 2 over the square root of x plus the square root of 2 is 1. You agree with that? Yes. Okay. On top, what do we get?
X minus 2.
Okay, on top, that's going to simplify to x minus 2. So what we have now is the limit as x approaches 2 of x minus 2 on top over x minus 2 times the square root of x plus the square root of 2. Now, why didn't I expand the bottom? Why didn't I multiply this times this when I did this? Yeah, the x minus 2's are going to cancel. So if I expanded it, it's taking away the option of canceling that out. So the x minus 2's are going to cancel. We're left with 1 on top. And can we use direct substitution now? Yes. So that's going to equal 1 over 2 square root of 2. Because we put 2 in for x, we get the square root of 2 plus the square root of 2 that's already there, and we get 2 square root of 2. Okay? We good with that? Does that make sense?
Yes.
Now let's go through this really quickly using the rules that we know for evaluating the derivative. So we're not going to use the limit definition. We're just going to evaluate the derivative at a point. What could we do first? How could we find the derivative of the square root of x? I'll give you a hint. I'm going to rewrite this. X to the 1/2. Okay, if we use exponents, it's easier to take derivatives. So the derivative at every point, f prime of x, is going to be what? 1/2 x to the negative 1/2. X to the negative 1/2 is the same thing as 1 over the square root of x. So what we get is 1 over 2 square root of x. So then if we want to know what f prime of 2 is, what do? Plug 2 in there and we get 1 over 2 square root of 2. So we know some tricks here, finding the derivative using the power rule to find the derivative at every point and then plug it in to do this a little bit faster, right? You agree with that? Okay, now if we are taking a test and it's a calculator section of the test and I want to evaluate the derivative of the square root function at 2, we're going to do this using a calculator. And I want to show you 2 different ways you can do this. Does anybody remember one way we can do it?
The end derivative.
Okay, so we're going to use the end deriv function. So if you have the TI-84 or the TI-83 of any version, you're going to look for the n deriv function. It's in the math menu. I believe it's in the second menu then. Is that right? Or no, it's in the first one. It's number 8. Number 8, yeah. So if you hit the math menu, hit number 8, it's going to give you the end deriv. Now, depending on how advanced your calculator is, it may give you something that looks like this. The more advanced ones, the TI-84 plus silver something or other not CX, but I'm not sure exactly what it is. But the more advanced ones, they're going to look like that. Now, most of you have a calculator that's not as advanced, doesn't do all that, but you have to enter all that same information. So where we had the variable of differentiation, the x, and the function, and the 2, the value at x that we want to evaluate the derivative, we're going to enter all that in. We're just going to enter it a slightly different way. So let me get rid of this here. I think. Nope. Right? So most of you just puts n deriv on the screen, puts an open parentheses, and then you have to know what to put in there. So the first thing we're going to put in is the function. Then you're going to put in a comma, and then you're going to put in, anybody know what comes next? Did you guys do this one already? What we need here is the variable that we're going to differentiate with respect to. Okay, this is, on that other one I showed you, it's going to be the d whatever variable we're differentiating with respect to. So in this case, it's going to be what? X. And then the last thing you're going to put in is what? Yeah, this is our c value here. I'm going to just call it c. That's the value that we want to evaluate the derivative at. And then we want to close the parentheses. Most of the time on your calculator, the closed parentheses doesn't matter unless you're going to put something else after it. So the function here we're going to enter, you could use the squared button, and it'll just put that in there. Or you could use a caret too. You guys know what a caret is?
Shouldn't it be root x?
Shouldn't
it be the square root of x?
Yeah, that's a good point. We should probably do that. So let's use the square root button, as Tilly reminded me that we're doing here. So we'll do the square root of x. Or we could do x to the 1/2 power, right? That would be okay too. So it'll look like that. Be sure you close this parentheses. That closed parentheses is really important. The variable we're differentiating with respect to is x, and then we want to do it at point 2. And what does it give us for our answer? 0.3535, and I'm just going to put ellipses there. So the calculator gives us this. What do you guys think about that? Is that a rational number? It actually kind of looks like it might be 35/99ths, right? If it repeats 353535, that would be 35 over 99. But
I know that.
well, now you do. It doesn't repeat 35353535, does it?
No.
So it's not a rational number. You're not going to be able to convert it to a fraction. But on a calculator portion of a test, you don't have to convert it to a fraction. You would just round it to the nearest thousandth, the nearest 3 decimal places, and you're done. In fact, there would be 2 acceptable answers here. Anybody know what they are? 0.354. That would be the rounded answer. Or the truncated answer would be 353. It's okay if you don't round and you just keep the thousandths place exactly the same. That would be truncating it. Truncate just means cut off. Or you could round that thousandths place. Now, if you were going to use this answer for something else later on, you would want to round to more decimal places, at least 5 or 6, and then use that answer rather than a rounded answer to the thousandths place. All right, any questions about this? How you're going to use the calculator? So I want you to do this one in the calculator then. Find the derivative of 4x minus x squared at -1. Help me out here. If you have the TI-83 or the older TI-84, what are we going to type in? I'll get the end deriv part. Okay, so 4x minus x squared. And you type that into your calculator and you get what? 6. It's pretty easy, isn't it? Just pops out with a number. Now, for something like this, the calculator is not really that helpful. In fact, in the time it took me to type that in, I could probably compute the derivative as 4 minus 2x and put -1 in for x and figure out that it's 4 minus -2, which is 6. And probably do all this in my head in the time that it takes me to type it into the calculator. What will be useful is when you have to take the derivative of a function that you don't know how to take the derivative of, or a complicated derivative or a complicated function that you don't really want to waste the time computing the derivative by hand and then plugging in values where you could just use the calculator to do it. Okay, this is one of the 4 things that you need to be able to do on a calculator. On the AP test, if you don't know how to do this, there will be questions that you won't get right if you don't know how to do this. So this is one of the things that you are expected to be able to do on a calculator. Okay, obviously they won't ask you to do this if it's not a calculator section. Yes?
Isn't there a way on the calculator, like if you type
So we're back on the first example that we did, and I want to do this graphically now. So I want you to go to the y equals, the equation editor part of your calculator. For most of you, it's just the y equals button, top left. For those of you that have the Inspire, it's slightly different. If you need help getting there, let me know. And I want you to enter the square root of x into your equation editor, and then I want you to go to the graph of it. And just hang on a second then. Once we have this graphed and in an appropriate window, then the next thing we want to do is evaluate the derivative. So just like before, we're going to go to the calc menu now, which is above the 4th button. So you want to hit second calc, and then I think it's the 6th entry on there, number 6, says dy dx, right? You guys agree with that? So now what this is doing is it's interpreting the derivative as a slope, because dy dx is a slope. So when we did the end deriv before, that was just a numerical derivative. It wasn't necessarily a slope, although we know we can interpret the derivative as a slope. So I want you to hit that button, hit the 6, or you can scroll down to it and hit enter, and then it's going to ask for an x value. When it asks for the x value, guess what you're going to type in? 2. So you type in 2, and what does it give you? It says dy dx equals 0.353535, whatever. Okay? Any questions about that? If you're taking a test and you're going to have to evaluate more than one derivative, it might be easier if you find it on the graph, because it's easier to use the same function over and over again to find the derivative at different points. If you're taking a test and you're only going to have to do it once, it might be easier to do it on the home screen and just enter the nDeriv function on the home screen. All right, it really doesn't matter which way. It's going to give you the same answer both times. And like I said, this is something that you're going to be expected to be able to do on the calculator portion of the AP test. All right, any questions about that? So I want you to go ahead and do, don't do that one, do this one. So I want you to do this one. I'll let you pick. If you want to do it on home screen, you can, or if you want to do it on the graph screen, you can. Either way.